Swayam Prabha. Digital India. Educated India.
So this is your prime tower, which is correspondingly deposited when material is switched between 1 or 2. And this was the exact location for that. So we will not discuss much about that because this is a dummy and maybe wasted only. But other than that, you can see now how our support is generated on the desired region, that is in the blue color, and the main material is deposited in the green color here. Also, you can see that the base plate addition utilizing the brim option was deposited. That is why this blue color on the base also you are seeing. So what is the purpose of it? Let me just try to explain this to you. As I have a support on the base side from the side of the base plate, when I deposit on the part, maybe on this portion, there will be less chance that the part is going to move in the XY plane. The brim support will support it from all the sides in such a way that it will make sure it is not going to move anywhere while depositing the material on top. However, of course, there is no large force we are applying, but due to the viscosity of the material itself, some drag is always there on the part that tries to move the part in the XY plane, which is undesirable. Because if it happens, then you may deposit the layers in shifted manner and you will never get the part exactly what you want. So now let us try to see the different layers and we will do the simulation as well. So you can see this right side bar can show you the different position of the deposited layers. So if I consider maybe a location over here, and then you can play this on the bottom side to see how the material is going to deposit at this particular layer. So first you can see it is depositing material here, and then it is depositing the main material here. So it makes sure that the material is always available for depositing the material onto the main object. So that is why it first deposited some material here on the prime tower and then it came back here. If there will be any switch, again the nozzle will go there and deposit the material. But unfortunately, right now in this layer there is no support mechanism, so you cannot see that. But we will consider a layer where there is a support as well. So you can see first it deposited 3 passes for the outer boundary by the contour parallel strategy that if you remember we have already considered in the shell criteria of the process parameters, and then it is filling the inside area by utilizing the zigzag strategy. So you can see the tool is moving back and forth utilizing the zigzag strategy. So let me move faster here now, and this is how the layer is completed. Now let me show you another layer which will have some support as well in between. So this is the one. Let me start it. So it is first, the nozzle is first depositing on the prime tower and then it is depositing on the base metal. And again the base material is deposited in 2 tool path. First few passes corresponding to the contour parallel strategy, and those are exactly in number 3 passes. I'll just show you that. So you can count 1, 2 and 3. It is currently depositing the third one. So after the third deposition out from the outer boundary, of course there will be the deposition corresponding to the outer boundary. Only 3 passes are there, 1, 2 and 3. And then it is depositing the inside area filling by utilizing the zigzag strategy. Then after that we know that this nozzle is going back to this prime tower, and here it will deposit some material from the extruder 2, because now it is going to deposit the support material. And now you see that, and it can be noticed that in this case right now the deposited material is not having the same area filling density as it was corresponding to this main material deposition. This is because I have already explained. Anyway, I am going to remove this support later on. So it is good to deposit this material always with the less infill density so that we can easily break it later on. So if we are happy with our toolpath, then we can definitely save to a file. And I'm going to create a folder here corresponding to this Ultimaker Cora file. And now if you want, yeah, so this has been saved here in this folder. This is your Ultimaker Cora ums5 underscore bracket r dot ufp file. If you want, you can save this project as well, and I'm saving it in the same folder. Also, now if you want, you can generate the G code. So I'm going to export the G code files here. As you see, I have selected the G code and I'm keeping the default name whatever it is giving. Now the G codes are also saved. So let me now show you the file corresponding to all three. So this is the file corresponding to the G code toolpath. It is written here. Now if I'll right click on this and open with Notepad++, definitely I can even read this file. And you see there are G codes available here. So you can use the same data to see on the NC viewer, but as there are huge lines, there are a lot of lines, it will be very difficult to see. So the G code file is ready to transfer to your machine to do the further thing. So this is all about the open source Ultimaker Cora. In the same principle, most of these freeware works. Those are typically used in additive manufacturing or in the 3D printing machines to deposit the material. The ultimate goal is always same. We have to get the corresponding G code files in the specified format corresponding to a 3D printer. So we know that in the case of directed energy deposition, there is a energy source which creates the molten pool in the substrate or pre-built layer, and then in that molten pool we feed the powder as a raw stock, or in some cases wire is also fed as a raw stock material. So now our aim will be to discuss about the utilization of a CAD-CAM package for generating the tool path for particularly for DED process, because the part we usually produce by DED undergo through a machining operation. That is why the CAD file, which is typically used as in the beginning to process the slicing and other steps, is not really the STL file. It is because anyway you are going to do the machining, and those STL files are not good to be the initial file for machining process. It is typically because you are going to do some approximation of the curved surfaces on the CAD file, and that will lead to some tessellation on the machining surface also. Therefore, usually the other formats are used, those utilizes the analytical curves to represent the boundary of the object. So for that purpose, we shall discuss about a package called Power Shape and Power Mill by Autodesk. So what you are seeing right now is the Power Shape, and there is another package called Power Mill. Power Shape is a CAD package and Power Mill is a CAM package. We usually do all the activities related to creation of the CAD file and any manipulation on the CAD file here in the CAD package, and then the generation of tool path and other such strategies usually happen in the Power Mill. So let us try to make the same part which we try to build by FDM process in the beginning, and then we'll consider a few complicated objects as well. So we have a CAD file of the bracket which is in the SolidWorks file. As you can see here, it's a SolidWorks part document, and I'm going to import this file into the Power Shape. It will take a few minutes to import the CAD model. So this is your CAD model. Now, as you can see, the surfaces are very smooth. This is because they are not represented by the STL format. So first of all, we should decide the build direction. So let me consider that we are going to build this part in this direction as you are seeing here. And therefore, typically this direction should be along the Z axis, while it is not the case here. Therefore, I have to rotate this part first. So to bring this build direction along the Z axis, I have to rotate this part by 90 degree about X axis. So here I'll select the part, select the axis about which I want to rotate, go to edit and rotate the part by 90 degree. So if I say that and say OK, you can see now the part has been rotated. So this is how its isometric view will look like. This is the Z axis as you see here, and this is the build direction as well. Now, of course, it will be difficult to make this whole without any support structure by DED. Definitely, we'll ignore that part right now. We will discuss later on with another example where these type of overhangs can also be realized. So I want to slice this object and create the toolpath for that. Now for that, let us build a substrate. So before building the substrate on which we are going to deposit this material, first we will select a work plane. So I am selecting this part and creating a work plane by using the option work plane here, and this work plane will be at the bottom of the selection, and it is at the center of the bottom of selection. Now I will create a solid that is nothing but a rectangular shape plate. So I'll click here so that the center of both are going to match, and now I'll click on this object solid 2 and right click here, modify its dimensions. I'll assume that its x-axis length is 120 so that it is outside the range of this base size of the object, and in a similar way let us consider it to be 300 mm long as well in y direction. If it is more, we can reduce it as well. So okay, 250 looks fine. Definitely you may need some portion of the substrate to clamp also, so you can accommodate all these variables here. Then the height of substrate I am assuming to be only 10 mm. Now if I just once have a look whether the substrate is fine, yeah, it looks fine. But here what is happening, the substrate is inside the object. If you are not going to utilize the substrate into the part, or you want to build few more parts on the substrate, then this substrate should be outside, not inward. Hence this part should move downward by 10 mm. It should not be exactly inside the object. So we'll do that. We'll again select this object and we'll go to edit and move this part in the Z direction by 10 mm. And as it's minus, so I'll write minus here. So as you can see now, the substrate has moved. Now on top of it, I'm going to build the part. So both the objects are ready. Now I'll save this part as a .ps model. That is the conventional model for the, that is the conventional file format for the power shape, and I'll save it in a folder. Let me call it as bracket power shape. So for that I'm writing ps. Now we shall transfer these objects into the power mill, and we will utilize the option of power mill that is called as the additive manufacturing module to create the toolpath. So first I will transfer this substrate. So this substrate I clicked on, I'll go to home and click on the button called power mill here. It will automatically transfer this part to power mill now. So here you can see the part has obtained. Also along with that, the work plane has also transferred, that is at the center of the substrate. Now we shall create a plane which will be corresponding to the slicing plane. It is recommended that you again go back to the power shape option and then first of all create another plane corresponding to the horizontal surface of the build object. So to make it more convenient, what I'll do first of all, I will just keep this substrate in level 0, this object in level 1, And I will now create, I'll just switch off this level 1 and I'll create one surface on top that will act as my slicing plane. So I'll go to surface, select the option plane and create a slicing plane. Now I'll just little bit extract it so that the plane is larger than the object. Now I'll just observe where the plane position is. It is quite low because we don't really want to build this substrate. We just want to build the object. So we will move this slicing plane above. For that again we'll do the same thing. We'll click, I have clicked on the plane, go to edit, go to the option move and move it in plus Z direction by 10 mm. As I said this, you can see the plane has been transferred at the top of the substrate. Now I will transfer this plane as well into another level, that is level number 2, and it has been stored in level 2. Now I will transfer this surface as well into the power mill. So I clicked on the surface, go to home and transfer it to power mill. As you can see, as soon as I clicked, it has transferred here in power mill and it is created as a new level in the level option. So the general is the substrate. This is your so I'll change the names also here. This is substrate, this is your slicing plane, and now we will bring our object as well. Before that, I'm going to save this project in the appropriate directory. So here I'm saving it as, calling it as toolpath for 3-axis DD. Now we are almost set and ready to bring our object as well here. We'll again go back to PowerShape and switch on now the level number 1 and switch off the other levels. Click on the object and transfer it to Power Mill again. So here you can see the object has also transferred. Now you can see here the third object has been transferred here. Its name is surface by default because that is the name given in PowerShape. So I'll modify it here to another name and I'm calling it as object. Now our next task is to create the toolpath. So let us first go to the option called additive on top of the Power Mill. Here there is an option called feature construction. We'll select this option and it will ask a few questions like what is your slicing plane, like your base. So our base is this surface and surface is nothing but this slicing plane. Then which feature we want to slice. So our aim is to slice only this object. So I'll select the object and other parameters like the tolerances. Tolerance means nothing but the deviation of your generated tool path between the from the desired one. So let us keep a high tolerance of 0.01. Focal length is nothing but the distance between your head and the melt pool. So in the case of laser based system, it is called as focal length. In the case of arc based system, it may be called as standoff distance. So it is just basically the distance between the head and the substrate which you want to keep in order to avoid any collision. So it should be 25 here, and that is where you are getting your appropriate melt pool size. Then bead width is nothing but the deposited bead geometry's width, how much width you are obtaining. Assume that it is 5 mm, default value written here. Then next is step over. So step over, we know already, it is nothing but the distance between two consecutive passes in the XY plane or in the deposition plane. So if I say 50% overlap, then the step over should be 2.5. Tool axis, let us consider it to be a lead and 0 0 right now because we are going to build only in Z direction. Other options are corresponding to the area filling strategy. So if you click here on the left side on the raster, so raster is the by default option available here for inside area filling. But if you have developed your own area filling strategies, there are ways of generating them also in PowerShape and PowerMill. It's a very powerful CAD-CAM package for that too, but let us right now focus on the raster strategy only. So if it is raster, it can be one-way raster or it can be two-way raster. One-way raster means it will just go from one direction to another direction and then it will lift and come back to new position and then deposit. If we consider two-way, it can have a connecting link between the two consecutive passes. So it's better to have two-way. In that way, we can save some time of deposition as well. Start from the lower left corner, or you can select other options as well. So lower left is the best one. Then the angle of the raster, let us assume it to be 45 degree. So it will deposit the material at a 45 degree from the in the XY plane. Rotation angle, it gives the rotation angle for each subsequent slide. If I say rotation angle as 10 degree, it means in the first plane, it will deposit the material at 45 degree angle, and then in the next plane, it will deposit by 55 degree angle, and then next 65 degrees, and so on. It will keep on changing the angle by adding 10 degree in that. So let us now consider these options for deposition. Next option is layering. It is saying offset from the base. No, we don't want to have any offset. We will start from the zero only. It is asking for the extent or the number of layers. So we can say height above the base or feature extent. So let us consider the feature extent wherever it is, till where the feature is, we will consider it to go there till that point. Layer thickness, of course, for time being, I will keep a very high layer thickness, that is 10 mm. You can even set the individual layer thickness also, and that is nothing but your adaptive slicing strategy, which you have already seen in last lecture. But we are not considering it right now because that will take more time, and you know that it can be done easily. If you look at this part, the adaptive slicing can be adopted in the overhang region or in the curved region like here. So this is the curved region and this is the overhang region. To appropriately create the part in overhang region or to create the part more accurately with the curved walls, you can consider the different layer thickness corresponding to the different height. But that option we are not considering right now, and keeping rest of the parameters same, I'll just calculate the toolpath. So it has created the toolpath. Now let us have a look how the toolpath looks like. For that, I'm going to switch off my object so that we can see the toolpath clearly. But still there are a lot of link paths here. Those are in the blue and red color. I don't want to see them as well. So I'll go to toolpath option and switch off the leads and links. Now you can see this is how your toolpath looks like. It is the toolpath corresponding to each and every slice. You can also do the volumetric simulation of this part while depositing the material here. Again, for that you can go to Additive tab and you can right click on your toolpath, say start simulation from the beginning and play it. So here you can see the tool is moving and appropriately showing you how it is going to deposit the material. You can also perform the volumetric simulation. So for that, I'll go to the tab Additive, and here there is an option called View Deposition. So if I'll click on View Deposition, starting from the base, if I say play, it will deposit the material and show you how it is going to deposit in the machine itself. So this is how your part will get deposited on the DED machine. Now, of course, by looking at the part itself, you can realize that the same part will require a machining operation also to create the final finished object. So this part itself can be exported as the raw stock for creating the machining tool path, and then using the same thing, same environment, same platform, you can create the machining tool path as well. There are several options for the tool path. So you can go to tool path, create the appropriate tool path for the machining strategy, like you want to do the 3D area clearance, model area clearance and all these strategies are corresponding to removing the material. So the major benefit of using such a CAD-CAM package is that you can utilize it for creating the toolpath for additive manufacturing as well as to create the toolpath for subtractive manufacturing. And that is how nowadays all the additive manufacturing system are going towards, they are going towards something called as hybrid manufacturing, and this is the best example for the CAPP of the hybrid manufacturing. Then of course, after generating this toolpath, you can right click here and create the individual NC program for the same. Then this is your NC program ready. Based on the machine you are using, you can use the appropriate post processor by utilizing this option here. Assume that I am using the Fanuc. I'll say accept and I'll switch off the coolant and all because that is not really required. Work plane 1 is fine, and I'm going to save this file into the toolpath which I created here. So I'll just copy this directory. And paste it here. Now let us see if it can write this toolpath. So the toolpath has written, and please note that now it is written for Fanuc controller, right? We'll close this, go back to our folder. So in this directory, you can find your toolpath called toolpath 3axis gd.tap. .tap is the default format which PowerMill creates for the Fanuc controller based toolpaths. So if I right click on this and open it with Notepad++, you can see the G codes written here. And they are corresponding to each and every slice. If you want to see this again in the NC viewer, you can check. So I'm going to paste this data here and let's see if I can plot it. So here it has been plotted. Of course, there are several links here. That is why it is not very clear to you. But if you will simulate it, then you will be able to see that. So let us try that. So there are several links here. That is why we are not able to see it. We can even hide the rapid motion tool paths. So let us try to build it and that it will be more clear. So this is the first layer. And you can see it is at 0, 0, right? And the next layer will be at another level. So this is corresponding to the next level. And you can see also the angle between the bottom raster toolpath and this one is the angle between these two raster passes is 10 degree because we said that in each layer the angle should change. Now this is the third layer and similarly it will deposit each and every layers here. So this is how you can create the toolpath by utilizing a commercial CAD-CAM package. Generally, if this type of additive option is not available in a CAD-CAM package, still you can use it for generating the toolpath. For that case, you need to just find out an appropriate method of creating the pocket milling toolpath in that CAD-CAM package. And then you can change that pocket milling toolpath to additive manufacturing toolpath. Yes, of course, you have to be very, very careful in such cases while creating the toolpath by such commercial CAD-CAM packages. Now let us consider another case in which the object shown here, which is already imported in power shape, need to be fabricated by directed energy deposition based additive manufacturing system. We already discussed that such a additive manufacturing system like DED do not use explicit support structures for fabricating the metallic objects. Instead, they utilizes the multi-axis kinematics of the machine tool to build the part in such a way that each time while depositing the feature, the droplet can fall along with the gravity. So let us try to develop the tool path for fabricating this object by directed energy deposition through a multi-axis kinematic machine tool. So first of all, we will decompose this part. Of course, after learning more about the process, you will be able to understand that which part has to be decomposed. But in this case, it is clearly visible that the center portion, which is right now highlighted in orange color, can be easily fabricated on 3-axis machine because it doesn't have any overhanging feature required. But these features, those are on the periphery, will definitely require some support. So let us first build this center part, which is easily manufacturable on a DED machine without any support structure. So for that, I have already created in different levels of the power shape the different features. Those has to be realized step by step. Our objective is first to build this center part, what you are seeing here, and it can be built on a substrate like this. Of course, there will be a slicing plane like this, a horizontal plane, which will slice from bottom to top. Already we have seen this for a very simple case as well. So let us now start transferring the data. First we will transfer this particular object to power mill. So I selected the object, transfer it to power mill. Now the object is here. Also a work plane has also transferred along with it, which is at the bottom center of the object. To see it, you can convert it to wireframe, and then you can see this is the work plane. Now I can import the substrate as well as the surface, which will utilize to slice the object and create the toolpath. So I'll go back to power shape, and now I'll switch off this and instead I'll switch it on, and I'll transfer this substrate as well as now I'll transfer this surface also, which will be my slicing plane. Let me save this right now. In an appropriate directory, and I'll give it a name like toolpath for multi-axis DED. So we are almost ready. As you can see here in your labels also, there is a surface which is corresponding to your main object or the center object. Let me rename it. So let me rename it to the center part. So I'm writing just as the center. Then the second is this substrate. So let us rename it to substrate. And then there is a surface here, which I'll call it as slicing plane 1. Now we shall utilize the same strategy like we did earlier. I'll go to the additive tab and choose the option named as feature construction. Now in the feature construction strategy, we can, like earlier, select the base, which is type of a plane, not cylindrical surface or arbitrary surface. Right now it's a planar base, and this is a surface which is a slicing plane name we have already given. The area filling strategies are raster, offset and profile. We have already seen raster, so let us consider this time the offset toolpath. And now let us consider the feature, which is nothing but a collection of surface and nothing but our center, which we have already defined. Other parameters like tolerance, I am going to keep 0.01 only. The focal length is 25 mm. That is nothing but the distance between the head and your substrate. Bead width is 5 mm. Step over is 2.5, meaning to say there are 50% overlaps between the consecutive deposition of the beads. Then we move to the next option, the strategy, that is offset. So there are two options for that. One is called as the median axis for the drive curve, and that can go from inside to outside or outside to inside. Let us consider the other parameters default. I'll go to the option layering now. In the layering option, we don't want any offset from the base, but we want to create the layers up to the top feature. Default layer thickness, let us keep to be 20 this time, because I want to create many layers so that quickly I can demonstrate it. And then press the button calculate. Rest of the options I'm not changing right now, but we can further explore to learn about the other options as well. Once I say calculate, it will take a few seconds to create the toolpath, as you are seeing here. So the toolpath has been created. Now to see the toolpath properly, I'll just switch off the center part, and also I'll just switch off the links and leads so that you can clearly see the deposited toolpath. It can be noted now in our case, the toolpath is not raster. It is offset from the outer contour only. Let me switch off the other contours also so that you can clearly see the toolpath. Now let us try to do the simulation so that we can see how it is going to deposit or add the material. So it will start from the bottom, as you see. Now all the passes are offsetted from the outer contour, and it uses a strategy called median axis, which is very popular nowadays, particularly for DED. So after completion, the entire layers, this is how it looks like. You can also simulate its volumetric simulation. For that, you can go to additive and view the deposition. So click here on view deposition and play. So this is how it will deposit the material. Also, if you want, you can change the strategy from contour offset to other strategies, like we can keep it again raster as well. So if it is raster, we can keep it either one-way raster or two-way raster. It is starting from the lower left corner and angle 45 and no rotation, or maybe you can keep some rotation maybe of 20 degree for each and every layers, and then again you can calculate. Now in that case, what will happen? Your contours will be almost same. The only difference will be they will be filled by the raster toolpath. Now this strategy we will look at from the deposition view. So this is how it is going to deposit the layers in each and every slice up to 300 mm, whatever the height of this cylindrical feature is. So once we have built this center part, now our objective will be to build those radial parts over here. So for that, we will go back to our power shape, and now we will import the other features there. Here now, it can be noted that the feature or the first slice is going to be cylindrical slice, and on top of it, of course, we are going to build these features. So this set of the surfaces will be the feature, and this center part will be going to be the slice. So it can be noted that in this particular case now, the horizontal plane is not going to be the slicing plane. It is going to be a circular shapes or the cylindrical shape surface, the slicing plane. So let us do that. Let us transfer this slicing surface first to power mill, and then let us also transfer these radial features to power mill. I am going to switch off this tool path for time being because we have to create another tool path now. So here you can see now both the slicing surface as well as the feature surfaces has been transferred. So let me change the name appropriately, and I'll call it as the slicing surface instead of slicing plane, and these radial features I'll call as the radial features only. Now let us try to develop the tool path for deposition of the material on this cylindrical surface. Of course, it is true that now your substrate has to be tilted for deposition the features on this cylindrical part. So as now, while depositing these features on this cylindrical surface, your tool axis will also change. Please remember that in power mill, all the time the tool is always aligned along the z axis. Therefore, now your work plane should also rotate in such a way that your Z axis is radially available and your axis of the cylinder is along the X axis. So that is very easy to do. I'll just select this surface first and I'll create a work plane again by utilizing the option home, create work plane, and I'm creating a work plane at the bottom of the surface. Now this work plane is having Z axis that is vertical, right? Or that is aligned with the axis of the cylindrical surface. And hence your tool will be, or the deposition gun will be always along with that. And that is what we don't want. So what I'll do, I'll rotate this by 90 degree about y axis in such a way that x axis will be aligned with the axis of this cylindrical surface. So for that, I'll right click on this work plane, go to transform and rotate it by 90 degrees. So I'll click on this y axis and I'm going to rotate it by 90 degree, and I want to rotate it in another direction. So minus 90 will work. Accept it. And now you can see the x axis is aligned along with the axis of the cylindrical surface, and now z axis is radially available for us. Now in that case, your tool direction will change while depositing the material. Hence it will be something like this. So it is already activated, this work plane, and now we'll create a tool path. So the work plane is already activated and it has appropriately aligned the object now to deposit these radial features, and now we will create the tool path. So tool path can be created in a similar way fashion. We'll go to additive, go to feature constructions, and this window for the feature construction will pop up. Now the first thing, for the base we will select, instead of plane we will select the cylinder now. And also my surface for slicing is not a plane which we selected earlier. Instead it will be a slicing surface, which is nothing but the cylindrical surface now. Also the features are these radial features and it is already selected here. The tolerances, focal distance, bead width and step over I'll keep same. Now let us move to the next option, that is for the strategy. I am considering the raster strategy only for area filling, and we'll go to the option for raster filling. One-way raster or two-way raster? Let us select the two-way raster because that can minimize the number of lifts. And then start with the minimum X, meaning to say starting from the closer to the work plane. Then rotation of the object can be in clockwise direction or in anti-clockwise direction as per our requirement. Let us consider, and then the direction along which it is going to deposit is across the axis of the cylinder, or it can be along also. So let us consider the across in that case. If you want, we can control the start point as well, and appropriately we can give the rotation within the layer. When the next layer is going to start, the start point may change. It is sometimes important because we don't want that the starting point to remain same in all the layers, because otherwise the errors those are usually obtained in the start and the end of the process may keep on accumulating and gives a very bad results in the end. So let us consider it as a default value. Now let us look at the options for the layering. We will create the layers. Those are of course offsetted to the base surface, that is a cylindrical layer, up to the feature extent. We want to create the layers up to this feature, which is towards the radially up to this point. And then the layer thickness, let us keep right now 20. It's a very high value of course, but just to give a demonstration I am using 20 so that the simulation can happen quickly. One more thing we have to be careful here now about the rapid moves, because now your tool has to go to the safe position so that there will not be any collision between the deposition head and the part you are depositing. So now you are depositing material onto a cylindrical surface, hence your rapid moves should be in such a way that your deposition head is at a safe location, and then you deposit the material on its periphery. So consider that now the rapid move should be cylindrical, and let us calculate it appropriately. It will calculate based on your deposition on the substrate, that each time after depositing anything on the substrate, it will move to the safe location. Already the height of the safe position of the deposition had from the center of this cylinder has been calculated automatically. Now keep the rest of the options same and calculate the tool path. It will take a few seconds to calculate it. So once the tool path is created, you can activate it from here or switch it on if it is off, and then you can see your tool path. So now one can notice that, let me just switch off this slicing feature and keep only the slicing plane on. I'll also switch off on the tool path, the links and the leads. And now you can see these are the tool paths corresponding to the deposition on this cylindrical substrate. If I do now the simulation from the start, you can see how it is going to deposit the material. We can also have a look at the volumetric simulation of the same. Fine. So this is all about the multi-axis toolpath generation by utilizing the commercial CAD-CAM package. You can also import your robotic arm in real here and see these deposition strategies. Let us try to do that as well. So assume that I have a Fanuc robot which is along with the robotic arm and a positioner, that is nothing but your XY table. And this is how it looks like. Now our objective will be first to deposit the center part. So let us have a look at the deposition strategy for creating the center portion. So now we can go to robot control, bring it to the home position, and then bring it to the tool attached with it. Make sure that the tool path is activated, and then you can press on the record. And now you can see your robot can move along with the tool path where you are depositing the material. And it is a one-way tool path, that is why it is depositing only in one direction and then lifting and coming back. You know that it is not a very efficient method of adding the material. So let me increase the speed of this so that you can see in the end that how it will deposit this center part first. Once the center part is created, now I'll activate the second part of the tool path. That will be of course on this center deposited feature. So for that you can see the robot has aligned itself appropriately. And now if this tool path is activated and I simulate it from the beginning, you can see how it is going to deposit this radial feature. So it can be easily seen now that the tool has been tilted for depositing or adding the material on the cylindrical surface. It can be also done in another way if we say that the priority should not be given to this robot to get tilted, but we should give the priority to tilt this table instead. Those type of things can also be done. Let us try to explore that as well. I am bringing my robot to the home position. So we are saying the joint which is corresponding to this turnitin table called as E1 will have more priority than the other ones. So I right clicked on that and say that they are on the high priority. So both these rotation of the substrate on the Turnitin table. So this rotation, that is the tilting, and this rotation which is corresponding to the rotary table, are having now more priority. If that is the case, now let us simulate it again, and you will find that now this table is also making some motions along with the robotic arm. So that is how you can utilize this commercial CAD-CAM package for generating the tool path for machining as well as additive manufacturing at the same platform. So with this, thank you very much.